Tonight, a comet discovered just 3 months ago reaches its closest point to the Sun, 857,000 kilometers from its surface, deep inside the solar corona. Hours before it arrived, the Sun's most dangerous active region fired an M7.5 flare from dead center on the solar disk, the strongest eruption in over a week and a fraction below X-class. This is happening while a G3 geomagnetic storm is already battering Earth. 4 astronauts are flying through deep space on the first crewed lunar mission in over 50 years, and the Molucca Sea is shaking with its strongest earthquake swarm in months. Something insane is happening near the Sun tonight, and the next 48 hours could determine whether this convergence becomes the most significant solar event of 2026. Hit subscribe and stay close, because this story is not finished. Region 4409 is still loaded. The comet's fate is still unknown. 4 astronauts are still out there beyond the shield, and the next 48 hours will tell us whether this was a near miss or just the beginning. This channel has been tracking this convergence for weeks. We will be here for whatever comes next. You will want to be here too. Now, let us get into it. At 1:17 in the morning, Coordinated Universal Time, April 4th, 2026, the Sun did something that made every space weather forecaster on the planet sit up straight. Active Region 4409, a complex magnetically tangled cluster of 18 sunspots spread across 200 millionths of the solar hemisphere, released a burst of X-ray energy that peaked at M7.5 on the solar flare scale. That is the strongest solar flare in over a week, and it is just 0.25 magnitude units below X-class on a logarithmic scale. To put that in everyday terms, this flare reached 75% of the way to the threshold where the classification changes from M to X, which is where the serious damage starts. The Space Weather Prediction Center immediately issued an R2 alert, meaning a moderate radio blackout swept across the entire sunlit side of Earth at the moment of the peak. High-frequency radio communications, the kind used by aviation, maritime operations, and emergency services, degraded or dropped entirely across parts of the Pacific and Asia. Now, M-class flares are not rare during solar maximum. The Sun produces dozens of them every month when it is this active. An M7.5 by itself would be noteworthy, but not alarming. It would make the daily reports, get flagged by space weather services, and be forgotten within a week. But this one is different. And the reason it is different has nothing to do with the strength of the flare. It has everything to do with where on the Sun it came from. Region 4409 sits at North 04, West 04 on the solar disk. If you are not familiar with solar coordinates, that means almost exactly dead center. Picture a dartboard. Region 4409 is the bullseye, and in solar physics, position is everything. A flare from the limb, the edge of the Sun, sends its energy sideways into space. It might produce a beautiful eruption in coronagraph imagery, but it misses Earth entirely. A flare from dead center is a different situation. Any coronal mass ejection, any CME, launched from North 04, West 04 would be aimed directly at this planet. Not glancing, not partial. Direct hit. A full halo CME from that position would arrive at Earth within 1 to 3 days, carrying the maximum possible magnetic payload. Now, the Space Weather Prediction Center noted in their latest discussion that no Earth-directed CME was observed in available coronagraph imagery from the M7.5 event. That sounds reassuring until you understand what it actually means. It means they checked the LASCO C2 and C3 coronagraphs aboard SOHO, the instrument that watches the Sun's outer atmosphere for expanding clouds of magnetized plasma. And they did not see an obvious eruption, But coronagraph imagery has limitations. A slow CME, a faint CME, or a CME that has not yet expanded enough to enter the field of view could appear in later frames. The absence of evidence in the first few hours is not evidence of absence. And even if this particular flare did not produce a CME, the region that produced it is not done. The full probability profile that the Space Weather Prediction Center assigned to region 4409 is sobering. 75% chance of a C-class flare, 35% chance of an M-class flare, and 15% chance of an X-class flare in any given 24-hour period. That 15% X-class probability is the highest of any active region on the solar disk right now. No other region comes close. Region 4405, the one that produced the X 1.4 on March 30th, currently sits at 5%. Region 4404 is even lower. Region 4409 is the threat. 15% might not sound like much until you frame it differently. That is roughly a 1 in 7 chance. Roll a die. If it comes up on one specific number, you get an X-class flare from the single most geoeffective position on the Sun, and region 4409 has been escalating. It produced an M 1.3 flare at 0756 UTC on April 3rd. Then another M 1.3 at 1250 UTC, 5 hours later. Then the M 7.5 at 0117 UTC on April 4th. 3 M-class flares in 18 hours, each one bigger than the last. That is not a region winding down. That is a region loading up. But the M 7.5 is not the only extraordinary thing happening near the Sun tonight. Because at almost exactly the same time this flare was firing, something else was arriving at the Sun. Something that has been on a collision course since January. 3 months ago, on January 13th, 2026, a team of 4 astronomers working in the Atacama Desert of Chile, Maury, Attard, Parrott, and Signoret, the MAPS team, discovered a faint smudge of light moving against the background stars. They cataloged it as C/2026A1. It was a comet, and its orbit told them something extraordinary about where it was headed. This comet was not just passing through the inner solar system. It was falling directly toward the Sun on a parabolic orbit, eccentricity of 1, with a perihelion distance so small that it would pass through the solar corona itself. Tonight, that arrival is happening. C/2026A1, also called MAPS after its discoverers, reaches perihelion on April 4th, 2026. Its closest approach to the Sun is 0.00573 astronomical units. In kilometers, that is approximately 857,000 kilometers from the Sun's center. Now, the Sun's radius is about 0.00465 astronomical units. So this comet's perihelion places it at roughly 1.23 solar radii from the center, meaning it passes just 0.23 solar radii above the photosphere. It is not near the Sun. It is inside the Sun's atmosphere, deep inside. At that distance, the comet is embedded in coronal plasma, where temperatures exceed 1 million degrees Kelvin. To appreciate how close this is, consider that the Parker Solar Probe, the fastest and closest solar observatory humanity has ever built, has a closest approach record of approximately 0.0435 astronomical units. This comet passes nearly 8 times closer than Parker has ever been. No spacecraft could survive where C/2026A1 is going tonight, and yet the comet might. C/2026A1 belongs to the Kreutz Sungrazer family, a group of comets that are all fragments of a single massive progenitor that broke apart centuries ago. Most Kreutz Sungrazers discovered by the SOHO spacecraft are tiny fragments that disintegrate entirely as they approach the Sun. They flare briefly in the coronagraph imagery and then vanish. But occasionally, a larger fragment survives the passage. The most famous example is Comet Lovejoy, C2011W3, which reached perihelion at 0.00555 astronomical units in December 2011. Lovejoy's perihelion distance is remarkably similar to C2026A, one's 0.00573 astronomical units. And Lovejoy survived. It emerged from behind the sun, battered and disrupted, but alive, trailing a spectacular reformed tail that became one of the most photographed comets of the decade. Whether C2026A1 survives depends on its size, its composition, and its rotational state. If it is large enough and structurally intact, it could emerge on the other side. If it is smaller or more fragile, it will disintegrate somewhere inside the corona, and that disintegration itself would produce valuable scientific data about the coronal environment at that depth. Either outcome is extraordinary. And at 0.00573 astronomical units, this comet sits in the top roughly 2% of all known cometary perihelion distances by proximity to the Sun. If you have been following this channel, you know this story. We first covered C2026A1 back in February. Video 23, the comet that could black out Earth. That video became the biggest in the Quiet Archivist's history, with over 102,000 views. We followed it up in video 28. Two comets are now heading for the Sun. Tonight is the payoff. The comet has arrived, and it arrived on the same day that the Sun's most dangerous active region decided to fire a near X-class flare from dead center on the disk. That timing is either a coincidence or a clue, and we will get to that question later. But there is something worth understanding about the Kreutz family and why this comet's survival matters so much. The original progenitor, the great comet that spawned all the Kreutz sungrazers, is believed to have been enormous, possibly one of the largest comets ever to visit the inner solar system. It broke apart during a perihelion passage centuries ago, possibly during the passage observed in 1106 AD, though the fragmentation may have occurred across multiple orbits. Every Kreutz sungrazer we see today is a piece of that original body. The SOHO spacecraft has discovered over 4,000 of them since 1995. Tiny fragments, most no larger than a house, that vaporize as they approach the Sun. They appear as bright streaks in the LASCO coronagraph and then simply vanish. C2026, A1 is different. It was discovered from the ground, not from SOHO, which means it is substantially brighter and almost certainly larger than the thousands of fragments SOHO picks up. The MAPS team spotted it from the Atacama, one of the darkest, driest observing sites on Earth, using techniques designed for faint near-Sun objects. The fact that it registered from the ground at all suggests a nucleus large enough to potentially survive the extreme conditions at perihelion. The question is how large? And until the coronagraph imagery arrives in the coming hours, we will not have a definitive answer. What we do know is that if C2026A1 breaks apart inside the corona, the debris will interact with the solar magnetic field in ways that could produce observable disturbances. Even a disintegrating comet deposits enormous quantities of dust, water vapor, and ionized material into the coronal plasma. At one point, 2-3 solar radii from the center, that material would be injected directly into the region where the coronal magnetic field is strongest and most structured. The scientific return, whether the comet lives or dies, is significant either way. But first, there is another layer to this story, because the M7.5 and the comet perihelion are not happening in isolation. They are happening against a backdrop that is already violent. 3 days before the M7.5 flare, on April 1st, the Sun launched a coronal mass ejection into space. That CME traveled outward at hundreds of kilometers per second, crossing the 93 million mile gap between the Sun and Earth. On April 3rd, at 15:03 UTC, it arrived. The instruments aboard the DSCOVR spacecraft, sitting at the L1 Lagrange point, roughly 1.5 million kilometers sunward of Earth, recorded the moment of impact. The total magnetic field strength spiked from 5 nanotesla to 14 nanotesla. The interplanetary magnetic field's north-south component, what space weather scientists call BZ, plunged to -11 nanotesla. Negative. Southward. And if you understand one thing about geomagnetic storms, understand this. Southward BZ is the key that unlocks Earth's magnetic shield. Earth's magnetic field points northward at the subsolar point, the point on the magnetosphere directly facing the Sun. The interplanetary magnetic field, carried by the solar wind, has its own orientation. When the solar wind's field also points north, the two fields repel each other. Earth's shield holds. But when the solar wind's field points south, -BZ, it connects with Earth's northward field through a process called magnetic reconnection. The field lines merge, and suddenly there is a direct channel from the solar wind into the magnetosphere. Energy floods in. Particles accelerate. The ring current intensifies, and the geomagnetic indices start climbing. A sustained southward BZ of -10 nanotesla or more is the signature of a significant geomagnetic storm. The April 3rd CME delivered -11. That was enough. The solar wind speed surged from around 625 kilometers per second to approximately 800 kilometers per second at the peak, then gradually declined towards 700. As of 0740 UTC on April 4th, the solar wind was still blowing at 627 kilometers per second. That is fast. Quiet solar wind sits around 300 to 400. This is a river moving at nearly double the usual speed. The result was a G3 geomagnetic storm, strong on the 5-level scale, with the planetary K index peaking at 6.67. That is the highest KP reading since the G3 event on March 21st through 22nd, just 2 weeks ago. The Space Weather Prediction Center extended a K6 warning through 0600 UTC on April 4th and issued a K5 alert at 0254 UTC, when the 3-hour synoptic period from midnight to 3 a.m. confirmed KP5, G1 conditions still active. 2 G3 storms within 14 days is consistent with what you would expect during solar maximum, but it is not average. Most years, even active ones, space a few weeks between G3 events. The Sun has been relentless in this stretch. What makes this particular storm more persistent than usual is its dual driver nature. It is not just the CME. There is also a negative polarity coronal hole high-speed stream, a CHHSS, reinforcing the solar wind from behind. Think of it like this. The CME was the initial punch, but the coronal hole stream is a sustained push that keeps the wind speed elevated long after the CME's magnetic cloud has passed. The Space Weather Prediction Center expects the enhanced solar wind environment to persist through April 6th. The forecast calls for G1 to G2 conditions through April 4th, G1 on April 5th, and active conditions on April 6th. Earth's magnetic field is not going to settle down anytime soon. The forecast calls for continued G1 to G2 conditions through April 4th, stepping down to G1 on April 5th, with active conditions persisting through April 6th. 3 more days of disturbed geomagnetic environment. 3 more days of elevated radiation belt flux. 3 more days of enhanced aurora at high latitudes, and 3 more days during which any new CME from region 4409 would arrive into an already weakened and disturbed magnetosphere, which is the worst possible starting condition for another impact. This storm has real consequences beyond the numbers. Geomagnetic disturbances at the G3 level induce currents in long conductors, power lines, pipelines, undersea cables. Grid operators in higher latitude regions monitor these events closely because geomagnetically induced currents can saturate transformers, leading to voltage instability and, in extreme cases, equipment damage. The March 1989 G5 storm knocked out power across the entire province of Quebec for 9 hours. We are not at G5 levels. But G3 is the threshold where the phone calls start happening at power utilities and satellite operators begin reviewing their contingency protocols. For satellite operators, the electron flux is the primary concern right now. At 4,465 PFU on the greater than 2 mega electron volt channel, the radiation belt environment is classified as high. Energetic electrons can penetrate satellite shielding and accumulate on internal components, causing electrostatic discharge events that can corrupt data or damage electronics. The geostationary orbit environment, where most communications and weather satellites live, is particularly vulnerable during these periods of enhanced electron flux. And there is one more thing about this storm: the aurora. Normally, a G3 storm at mid-latitudes produces visible aurora across northern Europe, Canada, and the northern United States. Reports have been coming in from observers across the United Kingdom, Scandinavia, and the northern tier of US states. The familiar green and purple curtains of charged particles colliding with oxygen and nitrogen in the upper atmosphere. But this time, the aurora was also visible from a place no human has ever seen it before, and that leads us to the human dimension of this story. Before we get to the aurora and the people who saw it, there is one more piece of this puzzle we need to understand. Because the M7.5 from Region 4409 is not an isolated event. It is the latest move in an escalation pattern that has been building for days. Here is the sequence. April 3rd, 0756, UTC M1.3 flare from Region 4409. April 3rd, 1250. UTC another M1.3. Almost identical in strength. 5 hours later. Then, April 4th, 0117, UTC M7.5. The jump from M1.3 to M7.5 represents a nearly six-fold increase in peak X-ray flux in the span of a single rotation of the Earth. That is not gradual. That is a region crossing a threshold. The magnetic classification tells the story. Region 4409 carries a beta-gamma designation, meaning its magnetic structure contains at least one pair of opposite polarity spots, close enough together that no clear boundary separates them. This creates a magnetic stress point, a location where magnetic field lines of opposite orientation are forced into close proximity. When that stress exceeds what the magnetic architecture can hold, reconnection occurs. The field lines snap and reform, releasing enormous amounts of energy as X-rays, ultraviolet radiation, and sometimes accelerated particles. The M7.5 was one such release. But if the underlying stress is not fully relieved, and the penumbral growth and spot consolidation suggest it is not, then another release is coming. Meanwhile, Region 4405, the source of the X1.4 flare, back on March 30th, is still on the disk at South 28, West 33. That X1.4 was a monster. It generated a Type 2 radio sweep, clocked at 1,872 kilometers per second, and an extraordinary 10 flare of 1,800 solar flux units. Region 4405 has quieted since then, but it remains a 10-spot complex with 5% X-class probability. It is rotating toward the western limb, losing its geoeffective edge, but it is not gone. The combined picture is this. The Sun currently has multiple active regions capable of significant eruptions. region 4409 at disk center with 15% X probability. Region 4405 rotating toward the limb but still carrying 5% X probability with 10 spots and 180 millionths of area. Region 4404 also contributing to the overall flare probability. The sun is not quiet. It is not settling down. It is in the thick of solar cycle 25, which has exceeded nearly every forecast made when the cycle began. We were told this would be a modest cycle, perhaps comparable to the relatively weak cycle 24. Instead, sunspot numbers have consistently overperformed. Flare rates have exceeded predictions, and the number of G3 or higher geomagnetic storms in 2025 and 2026 has been notably above the average for this phase of any cycle. The Space Weather Prediction Center forecasts a 55% probability of R1 to R2 radio blackouts through April 6th, with a 15% chance of R3 events. Those numbers mean that more flares are coming. The question is, how big? If region 4409 produces an X-class flare, and there is a 1 in 7 chance of that on any given day, and that flare launches a full halo CME from its dead center position, the geomagnetic consequences could exceed the G3 we have already seen. We could be talking about G4, possibly higher, and if it produces a major solar particle event, a flood of high-energy protons, then the consequences extend beyond Earth's magnetic field. Because there are people out there right now, beyond the shield. On April 1st, 2026, the same day the CME that is currently battering Earth left the Sun, NASA launched Artemis 2. 4 astronauts aboard the Orion spacecraft, commanded by Reed Wiseman, lifted off on the most ambitious crewed space mission in over 50 years. This is the first time human beings have traveled beyond low Earth orbit since Apollo 17 splashed down in December of 1972. For the first time in more than half a century, there are people in deep space, and they launched straight into this. In low Earth orbit, where the International Space Station operates, where every crewed mission for the past 5 decades has stayed, astronauts are protected by Earth's magnetosphere. The magnetic field deflects most solar energetic particles and traps them in the Van Allen radiation belts. It is not perfect protection, but it is substantial. Astronauts on the ISS receive elevated radiation exposure compared to people on the surface, but the magnetosphere does the heavy lifting. In deep space, there is no magnetosphere. The crew of Artemis 2 is beyond the shield. They crossed that invisible boundary, the magnetopause, roughly 65,000 kilometers from Earth on the sunward side, and continued outward into interplanetary space, where the only thing between them and the sun's particle output is the spacecraft itself. The Orion capsule provides some shielding through its aluminum-lithium alloy hull and internal structural components. The AstroRad radiation vest, a wearable garment designed to protect vital organs, was tested with anthropomorphic measurement phantoms during the uncrewed Artemis 1 mission, providing baseline data on dose reduction. But no human crew has ever worn it during an actual solar storm in deep space. Artemis 2 is the first real test. Think about what that means. The shielding was validated using mannequins and models. The radiation environment was projected using historical data and probability distributions. But the actual test, a human crew in deep space, during a solar maximum that has exceeded predictions, with a disk center active region firing escalating flares, is happening right now, for the first time, with no option to abort if conditions worsen beyond what the models anticipated. That is the nature of exploration. You build the best spacecraft you can. You assess the risks as honestly as you know how, and then you go. The crew of Artemis 2 understood this when they climbed into the capsule. But understanding a risk intellectually and experiencing it physically are different things, especially when you can see the storm with your own eyes through the window. The radiation data during this transit tells a concerning story. The greater than 10 mega-electron-volt proton flux peaked at 6.02 particles per flux unit on April 3rd at 0830 UTC. The S1 radiation storm threshold is 10 PFU. That means the proton flux reached 60% of the formal storm threshold. Not enough to trigger an official radiation storm warning, but absolutely non-trivial for crew members who have no planetary magnetic field between them and those protons. The greater than 1 mega-electron-volt proton flux peaked near 3000 PFU, indicating a substantial energetic particle population in the inner magnetosphere. And the greater than 2 megavolt electron flux hit 4465 PFU, classified as high, indicating ongoing radiation belt enhancement. The S1 probability for April 4th through 6th is 15%. That is driven entirely by the flare potential of regions 4404, 4405, and 4409. If any of them produces a major flare with an associated proton event, the crew would be directly exposed. NASA announced the Artemis 2 science officers, Kelsey Young, Trevor Graff, and Angela Garcia, while the mission was already in flight. The public narrative from NASA has been professional and measured. No alarmism, no mention of elevated risk, but the data is the data. The crew is in deep space during an active G3 storm, with a disk center active region rated at 15% X-class probability, and proton flux that has already reached 60% of storm threshold. If you have been watching this channel, videos 54, 55, and 57, you know we have been tracking this risk since before the launch. The scenario we warned about is not hypothetical anymore. It is happening. On April 3rd, NASA released an image that will likely define this mission in public memory, regardless of what happens next. Commander Reed Wiseman, looking out the window of the Orion spacecraft somewhere between Earth and the Moon, photographed two auroras visible simultaneously. Two shimmering curtains of charged particles slamming into Earth's upper atmosphere, glowing green and violet, captured from a vantage point that no human being has ever occupied during an active geomagnetic storm. It is the first time in the history of crewed spaceflight that auroras have been documented from a cislunar trajectory during storm conditions. Think about that for a moment. In the entire history of human spaceflight, from Yuri Gagarin in 1961 through every space shuttle mission, every Soyuz, every SpaceX Dragon, no human being has ever been in a position to photograph an aurora from cislunar space during an active geomagnetic storm. The ISS orbits at about 400 kilometers altitude, well within the magnetosphere. The Apollo missions flew to the Moon and back, but none of them transited during storm conditions that produced visible aurora at the spacecraft's position. Wiseman's photograph is literally a first. It has no precedent. And the fact that it exists is a direct consequence of launching a crewed mission during solar maximum. The photograph is beautiful, and it is also revealing in ways that go beyond aesthetics. What you are seeing in that image is direct visual proof that the Orion spacecraft is immersed in the same energetic particle environment that is lighting up Earth's atmosphere. The aurora is caused by solar wind particles funneling along magnetic field lines and colliding with atmospheric gases. Wiseman can see those particles hitting Earth because those same particles are passing through the space his spacecraft occupies, only without a magnetic field to deflect them. NASA's decision to release the photograph is, in a sense, a double-edged transparency. It shows the public that the agency is not hiding the geomagnetic activity. It is right there, visible from the spacecraft window. But it also shows anyone paying attention that the crew is flying through an active solar storm. The optical proof is in the image itself. And this is where we need to talk about history. Because the scenario unfolding right now a crewed deep space mission during active solar storming, has exactly one historical parallel, and it is one that haunts every space weather scientist who works on human spaceflight safety. In August of 1972, between the Apollo 16 mission in April and the Apollo 17 mission in December, the Sun produced one of the most intense solar particle events ever recorded. If a crew had been on the lunar surface or in transit during that event, the projected radiation dose was 241 rem per hour, with a cumulative exposure estimate of 358 rem. NASA's current career dose limit for astronauts, updated in 2022 under NASA Standard 3001, is 600 millisieverts. The 1972 event would have exceeded that limit in a matter of hours. It did not hit anyone because no one was out there. The timing was pure luck. The Artemis II crew is out there now. And the Russell-McFerrin equinox effect, a well-documented seasonal vulnerability in Earth's magnetic coupling with the solar wind that peaks around the equinoxes, means that early April falls within the tail end of the spring vulnerability window. The conditions for enhanced geomagnetic disturbance are structurally elevated right now regardless of what individual active regions do. Across a 9+ day mission, the cumulative probability of at least one X-class flare from region 4409 alone, at 15% daily, starts to add up. Factor in regions 4404 and 4405, each carrying their own flare probabilities, and the mission is threading a statistical needle. Not a guaranteed crisis, not even a probable one, but a non-negligible one. And unlike the International Space Station, where crew can shelter in more heavily shielded modules, or unlike a ground-based population that has an entire magnetic field and atmosphere for protection, the Artemis II crew has the Orion hull and the Astrorad vest. That is their margin, and they cannot come home early. The trajectory is set. The physics of orbital mechanics does not allow a quick return from cislunar space. A free return trajectory from cislunar space takes days, not hours. Whatever the Sun does in the next several days, those 4 people are along for the ride. Every flare from region 4409, every proton event, every enhancement in the radiation belt, they will experience it all from their aluminum and composite cocoon, somewhere between here and the moon, with nothing but engineering and probability between them and a worst-case scenario that we barely avoided in 1972 by sheer calendar luck. The Artemis 1 heat shield anomaly adds an uncomfortable footnote. During the uncrewed test flight in late 2022, the Orion capsule's heat shield experienced unexpected charring and material loss during re-entry, damage that was not fully predicted by models. NASA investigated, made modifications, and cleared Artemis II for flight. But the fact that the first flight revealed something the models missed lingers in the background of every mission discussion. If the heat shield behavior was not fully understood, what else might the models have underestimated? The radiation shielding has been tested with phantoms, but never with living humans in deep space during an actual solar storm. This mission is the test. Let us return to C-2026-A1. Because the question of what happens when this comet transits, the solar corona is not just academic. It could produce some of the most extraordinary solar observations of the year. The interaction between a comet and the solar corona is one of the least understood phenomena in solar physics, largely because it almost never happens in a way we can observe in detail. Most sun grazers are too small and too faint to track through the dense coronal environment. They appear as dim streaks in coronagraph imagery and vanish. But occasionally, a comet large enough and bright enough to survive, or at least partially survive, the transit provides an unprecedented natural laboratory. When Comet Lovejoy passed through the corona in December of 2011, the Solar Dynamics Observatory and the SOHO spacecraft captured something scientists had never observed directly before. As Lovejoy plunged through the coronal plasma, its ion tail, the stream of charged particles being stripped from the comet by the solar wind, began to oscillate. The tail was being deflected and redirected by the coronal magnetic field, swaying back and forth like a flag in a shifting wind. Those oscillations were not random. They were responding to the local magnetic field structure, and by analyzing the frequency and amplitude of the tail movements, researchers were able to derive the strength of the coronal magnetic field at the comet's location, approximately 6 Gauss at closest approach. It was the first time anyone had measured the coronal magnetic field using a comet as a natural probe. If C-2026-A1 survives perihelion, the opportunity for similar, or more dramatic, observations is immense, and there is a critical difference between 2011 and now. When Lovejoy made its passage, the Sun was in solar cycle 24, which was historically weak. The solar magnetic environment was relatively subdued. Solar cycle 25 is a different beast entirely. The current cycle has overperformed nearly every prediction. The Sun's magnetic field is more complex, more active, and more energetic than what Lovejoy encountered. If C-2026-A1's tail interacts with this more turbulent corona, the oscillation data could reveal magnetic field structures that have never been measured at this depth during a solar maximum. The Comet CME interaction hypothesis adds another layer. In 2011, researchers documented a temporal correlation between Kreutz sungrazer passages and CME activity. Some scientists noted that CMEs appeared to increase in frequency around the time sungrazers were transiting the corona. The mainstream scientific position is clear. This is coincidental. The Sun produces CMS frequently during solar maximum, regardless of whether a comet is present. Flares and CMEs originate from magnetic reconnection in active regions, a process driven entirely by the Sun's internal magnetic dynamics. A small comet has no meaningful gravitational or magnetic influence on a star, but the mechanism of cometary material interacting with coronal magnetic field lines is not fully understood. A comet transiting the corona deposits ions, dust, and neutral gas into a magnetically active environment. Could a sufficiently large deposit of cometary material destabilize a pre-existing magnetic configuration that was already on the edge of erupting? The established answer is almost certainly no, but almost certainly is not definitively, and the fact that the M7.5 fired from region 4409 within hours of C-2026. A1's closest approach is the kind of temporal coincidence that makes even careful scientists pause before dismissing it entirely. The responsible framing is this: we cannot prove the comet caused the flare. The physics says it did not. The flare originated from magnetic reconnection in region 4409's beta-gamma magnetic field, a process that was building through 3 escalating events over 18 hours, well before the comet reached its closest point. But the timing is what it is, and nature occasionally produces coincidences that look like causation to the human eye. That does not make them causal. It makes them worth documenting. What matters now is the SOHO LASCO C2 and C3 coronagraph imagery over the next 12 to 24 hours. If the coronagraphs capture C-2026-A1 entering the field of view alongside CME activity from any active region, those frames will become some of the most shared solar images of the year. If the imagery shows the comet disintegrating, a bright flare followed by a fading tail, and then nothing, that is a different, but equally dramatic story. And if the comet simply does not appear in the coronagraphs, either too faint to detect or already destroyed before reaching the field of view, the absence will itself generate speculation about data suppression. Every outcome here produces a story. There is one more speculative angle worth addressing because viewers will raise it regardless. The idea that a comet transiting the corona could somehow trigger a coronal mass ejection that would then strike Earth. A comet-induced blackout scenario. This was the core premise of Video 23, which explored whether C-2026 A1's perihelion could coincide with a CME aimed at Earth. At the time, we noted that the scientific basis was thin, but the timing was dramatic. Here we are, on the day of perihelion, and the Sun has indeed produced a significant flare from its most geoeffective region within hours of the comet's closest approach. The comet did not cause the flare. But the fact that both events are happening simultaneously will be nearly impossible to separate in the public imagination. And honestly, the science is not so airtight that we can dismiss every possible interaction mechanism with absolute certainty. What we can say is that the balance of evidence strongly favors coincidence. What we cannot say is that we understand every detail of how cometary material behaves inside a magnetically active corona at solar maximum. Those are two different statements, and intellectual honesty requires holding both. There is one more thread we need to pull before we bring this all together. While the M7.5 was firing, while the comet was entering the corona, while the G3 storm was battering Earth, and while 4 astronauts were floating through deep space, the Molucca Sea was shaking. The Molucca Sea, located between the northern arms of Sulawesi in Indonesia, sits in one of the most tectonically complex zones on the planet. It is a plate collision zone where multiple tectonic plates converge, producing frequent and sometimes intense seismic activity. Since April 2nd, the region has produced at least 20 events at magnitude 4.5 or above in just 12 hours, including an M5.9, an M5.8, and an M5.6. The swarm has continued into April 4th with new significant events. The Molucca Sea's tectonic setting is fascinating in its own right. It is one of the only places on Earth where 2 oceanic plates are colliding head-on, rather than one subducting beneath the other in a clean, well-defined trench. The result is a chaotic collision zone where earthquakes occur at a range of depths and in a variety of orientations, making the region one of the most seismically energetic places on the planet relative to its size. Swarms here are not unusual. Sequences of magnitude 4 and 5 events can persist for days or weeks as stress redistributes along the tangled network of faults. What draws attention this time is the timing. This swarm has been running concurrently with the geomagnetic storm that escalated from G2 to G3 conditions between April 2nd and 4th. And this is not the first time the Quiet Archivist has noted this pattern. The Tonga M7.5 earthquake on March 24th, covered in Video 51, occurred during a G3 storm window. The Vanuatu M7.3 on March 30th, Video 55, coincided with the G2 storm that followed the X1.4 flare. The framework for evaluating these overlaps comes from Marchitelli and colleagues, published in 2020. Their study found a statistical correlation between increases in solar proton density and the occurrence of M5.6 or larger earthquakes within 24 hours of geomagnetic disturbances. The framework does not claim causation. It documents a pattern, and the proposed mechanism that variations in the solar wind's proton density could influence the Earth's crustal stress through electromagnetic coupling remains debated. Most seismologists are skeptical. The Earth's crust is governed by tectonic forces accumulated over years and decades, not by fluctuations in the solar wind over hours. But the pattern keeps showing up. 137 M4.5 or above earthquakes have been recorded globally in the past 7 days alone. The Molucca Sea swarm's persistence through the April 2nd through 4th geomagnetic storming period is consistent with the Marchitelli framework, even if it does not prove it. And the viewers watching this channel know the pattern. We have documented it in Video 46. Video 48, Video 51, Video 55. The data is the data. The causation is the open question. We should also note briefly that asteroid 2023 DZ2 made its closest approach to Earth on April 4th at 2.63 lunar distances, traveling at 7.24 kilometers per second. It is a known object, discovered in 2023, estimated in the tens of meters size range based on its absolute magnitude of h equals 24.28. The flyby is routine from a hazard perspective, but it happened on the same date as everything else: the Comet perihelion, the M7.5, the G3 storm, the Artemis 2 transit, the earthquake swarm. Same day. The conspiracy angle here is obvious and will be widespread. The "everything is connected" framing is at its most potent today, and social media will run with it. Claims that the comet triggered the flare, that the flare triggered the earthquakes, that the earthquakes are a sign of something bigger. These narratives will circulate within hours of this video going live. Some of them will include claims about government suppression of data, or about agencies hiding the true severity of the events. The SOHO LASCO imagery will be scrutinized frame by frame. If there is any gap in the data, any period where coronagraph images are missing or delayed, which happens routinely for technical reasons, that gap will be interpreted as evidence of a cover-up. The temptation to draw a line through all of these events is powerful, and the honest answer is, some of those connections are real physics, and some are coincidence. Solar geomagnetic coupling is real and well documented. CMEs hit Earth's magnetic field and cause storms. Full stop. The physics is understood. The models are validated. The predictions are reliable within known error bars. Solar seismic coupling is debated. There is a statistical signal in the literature, most notably the Marcatelli 2020 paper, but no proven physical mechanism that explains how solar wind variations could trigger earthquakes through tens of kilometers of rock. The proposed mechanisms: electromagnetic coupling to the crust, variations in Earth's rotation rate, changes in groundwater pore pressure from geomagnetically induced currents, are all speculative, and none have been confirmed experimentally. Comet flare coupling is not supported by current physics. The Sun is 1 billion times more massive than any comet. Its magnetic field dynamics are driven by internal convective processes on scales that make a comet about as significant as a grain of sand dropped into the ocean during a hurricane. And the asteroid flyby has nothing to do with any of it. It is a known object on a well-characterized orbit that happens to pass by on the same date. But nature does not care about our categories. It delivered all of this on the same day, and it is up to us to sort out which threads are physics and which are chance. The honest position is this: we know more than we did 10 years ago about all of these systems. We also know how much we still do not understand. The intersection of solar activity, seismic activity, cometary physics, and deep space human exposure is a frontier where established science, emerging research, and speculation all coexist. The responsible approach is to present all three clearly and let the audience decide where their comfort level sits. So where does this leave us? What happens next? Region 44, O9, sits at the most geoeffective position on the solar disk. It has escalated through 3 M-class flares in 18 hours. It carries a 15% X-class probability, 1 in 7, on any given day. Its magnetic classification shows ongoing stress buildup. The penumbra is growing. The spots are consolidating. This is not a region that has exhausted itself. If anything, the M7.5 may have been a partial energy release, enough to light up the X-ray detectors, but not enough to fully relieve the accumulated magnetic tension. The answer splits into 3 scenarios, and each one tells a very different story about what kind of day, April 4th, 2026 turns out to be. Scenario 1. Escalation. If Region 4409 produces an X-class flare with an Earth-directed CME from its current position, the geomagnetic impact would almost certainly exceed the G3 conditions we have already experienced. A fast CME from disk center, and fast in this context means 1,000 to 2,000 kilometers per second, which is plausible given that the X1.4 from Region 4405 just 5 days ago produced a Type 2 shock at 1,872, could arrive at Earth within 18 to 36 hours. The compressed transit time matters because a faster CME packs more kinetic energy and typically carries a stronger magnetic field. If it arrives with sustained southward BZ, which is partly a matter of chance, depending on the CME's internal magnetic structure, it could potentially drive KP to 7 or higher. G4 conditions, perhaps even G5 if the CME is exceptionally fast, if the BZ stays deeply negative for hours, and if it arrives while the current disturbance has not fully subsided. A scenario called CME on CME stacking, where a new eruption plows through the disturbed solar wind left by the previous one, compressing and accelerating. That would put us in territory where power grid operators go on high alert, where satellite operators begin safing sensitive instruments, and where aurora becomes visible at latitudes as far south as the Gulf Coast of the United States. If the same flare produces a significant solar particle event, a flood of high-energy protons, then the calculus changes for the Artemis II crew. The greater than 10 mega-electron-volt proton flux, which has been hovering below the S1 threshold, could spike dramatically. A major SPE from a disk center region during the Russell-McFerrin vulnerability window is the worst-case scenario for unshielded deep space operations. It is the August 1972 scenario revisited, except this time, there are people out there. The crew would have to shelter in the most heavily shielded section of the Orion capsule and wait for the particle flux to subside. And depending on the event's magnitude, even that might not be fully adequate. Scenario 2. Sustained threat. Region 4409 continues producing M-class flares without crossing into X territory. The geomagnetic environment remains disturbed at G1 to G2 levels for several more days. The proton flux stays elevated but below S1, and the Artemis II crew completes their mission under sustained but manageable radiation exposure. This is arguably the most likely outcome. Solar active regions often produce sequences of moderate flares without ever reaching their maximum theoretical output. The energy dissipates gradually rather than catastrophically. But most likely is not certain, and the 15% daily X-class probability means you are rolling that 1 in 7 die every single day the region remains on the visible disk. Scenario 3. The near miss. If Region 4409 does not produce another major flare, if the M7.5 was the peak and the region begins to decay, then today becomes something different, a near miss story. The day when a comet entered the corona, a near X-class flare fired from dead center, a G3 storm-battered Earth. 4 astronauts flew through deep space, and the Molucca Sea shook with its strongest swarm in months, and nothing catastrophic came of it. Just nature running all its programs at once, and humanity passing through the needle. Near-miss stories are the ones we tend to forget. The August 1972 SPE is famous only among space weather researchers precisely because it missed everyone. No crew was exposed. No dramatic footage exists. No headlines ran. The fact that it could have been a disaster only matters in retrospect. If April 4th, 2026 ends the same way, a day of extraordinary convergence that never quite tipped into crisis, we will probably forget it too. That is the nature of near misses. They only become important stories when the next one is not a miss. C 2026. A1's fate will be resolved in hours. Perhaps, by the time you are watching this, we already know the answer. The SOHO LASCO coronagraph data is the definitive source. If the comet survived perihelion, we will see a reformed tail emerging from behind the solar disk, a bright streak pushing outward through the corona, oscillating in the magnetic field, just as Lovejoy's did in 2011. If it disintegrated, there may be a brief brightening, followed by nothing. The comet consumed by the very star it was falling toward. Either way, this chapter of the story reaches its conclusion tonight. We should also note for completeness that Arctic sea ice just tied a record low for the month of March 2026. This is not directly connected to the solar comet flare convergence, but it adds another data point to the broader picture of Earth systems under stress. The ice extent at the poles responds to long-term climate forcing, not to individual solar storms. But the fact that the cryosphere, the magnetosphere, the lithosphere, and the heliosphere are all producing anomalous readings in the same calendar week is the kind of coincidence that makes systems thinkers uncomfortable. Not because they are causally connected, but because it reminds us how many systems we are monitoring simultaneously and how rarely we zoom out far enough to see them all at once. There is an irony worth noting. The European Space Agency and the Chinese Academy of Sciences are preparing to launch the SMILE satellite on April 9th, 5 days from now. SMILE is designed specifically to study how the solar wind interacts with Earth's magnetosphere. The instruments that will help us understand events exactly like the one happening today are being launched while the event is already occurring. The tools to study the phenomenon are still on the ground while the phenomenon rages overhead. And perhaps that is the honest summary of where we stand in 2026. We are deep into solar cycle 25, which has exceeded every prediction. We have sent humans into deep space for the first time in over half a century, directly into the teeth of a solar maximum that we did not fully anticipate. A comet discovered 3 months ago is transiting the corona of our star tonight. The sun's most dangerous active region is aimed directly at us with a loaded magnetic field. The geomagnetic storm from 3 days ago has not even finished yet. Arctic sea ice, as a brief footnote, just tied a record low for March 2026. The systems that govern our planet, solar, orbital, tectonic, climatic, usually operate on their own timelines, in their own domains, indifferent to each other. But occasionally, they converge. Not because one caused the other. Not because there is a grand mechanism connecting comets to earthquakes or flares to tidal forces. They converge because all of these systems are always running, and probability says that sometimes they will all deliver their most dramatic moments on the same calendar page. April 4th, 2026 is that page. The real question is not whether the comet caused the flare. It almost certainly did not. The real question is not whether the storm triggered the earthquakes. That remains genuinely unresolved, but is probably coincidence. The real question is what Region 4409 does in the next 48 hours. Because if the answer is nothing, if it quiets down, if the magnetic tension relaxes, if the spots begin to decay, then this was just a remarkable day. But if the answer is an X-class flare from dead center on the disk, aimed at Earth with 4 humans in deep space and a geomagnetic field already battered from 3 days of continuous storming, then we are looking at the most significant solar event of 2026. And somewhere between here and the moon, 4 astronauts are looking out the window at an aurora they were never supposed to see from that angle. The comet they are sharing the sky with is either burning alive inside the corona or threading the same impossible needle they are. And the active region that fired 3 flares in 18 hours is rotating slowly, imperceptibly, carrying its loaded magnetic field across the face of the sun, still pointed directly at Earth. Still at 15%, still 1 in 7. The next 48 hours have not started yet.